Alright, let's take a look at a little implicit differentiation today. Okay, so we're going to try to take the derivative of an equation that looks like this, alright, which is very different from the ones we've done in the past where it's just y equals. Here we have x's and y's all jumbled up, and a lot of times we'll use implicit differentiation in equations that are not functions. Alright, so for example, a circle is not a function, because a circle fails the vertical line test, right? And it's going to turn out, I don't expect you to know what this looks like without graphing it, but it's actually going to be an ellipse. You might remember from pre-calculus, ellipse often happens when you have an x squared and a y squared term, and then some stretching terms in there too. So this is actually going to be an ellipse, but I don't expect you to know that. But what I do expect you to be able to do is find what dy dx equals. I remember what we're doing is finding the slope of the tangent line. Remember that's what dy dx is, right? The change in the vertical direction over the change in the horizontal direction, right? Rise over run. So we're just finding the slope. All right, so here's the procedure. We're going to do problem number 21 on page 163. We're going to work our way through, and what we need to be careful about is remembering that the derivative of y is not what we're taking the derivative with respect to. We're taking the derivative with respect to x. And so y is a function of x. So we got to keep that in mind when we take the derivative of y. I'll show you how to do that in a second. All right, let's start with this first term, which is very easy. The derivative of this first term with respect to x is going to be 12x. All right, now the second term is more difficult because we have three different factors here, right? 3, x, and y. The 3 you could pull out front, but how I usually like to do these, and it's up to you, I'll show you the other way in class, is I call the first factor 3x and the second factor just y. When I have two factors I want to take the derivative of, I need to use the product rule. Alright, so remember the product rule. First factor times the derivative of the second factor. Remember, the derivative of y is not 1. The derivative of y with respect to x is going to be dy dx. I'm going to use y prime just to make the notation a little bit simpler. Alright, so that's the first part of the product rule. Then the second factor times the derivative of the first factor. And the derivative of 3x with respect to x is just 3. Alright, now let's move on to the third term. Is going to be 4y. But be careful here, there's some chain rule. It's going to be 4y times the derivative of y, which is y prime. We'll talk more about why that is in class, but remember y could have some x's in it. So y is a function, so we need to, or could be a function, so we need to consider that there are some x's in there. Alright, then the derivative of 17y is not just 17, it's 17y prime. The derivative of 6 is going to be 0, and the derivative of 0 is 0. Alright, so there's our first step, and that's really the really hard part of implicit differentiation. Alright, you got to remember when you're taking the derivative of y's, they're actually y primes, plus there's this really tricky term in here that has some product rule. Okay, so let's see, we probably could just substitute in here because they're asking us for the tangent line through the point -1, 0. So we could go ahead and plug in -1 for x now and 0 for y now and then solve for y prime. But a lot of times they ask us to figure out what dy dx is, and so I want to show you the procedure for that too. Alright, so what I like to do is gather all the terms that have y prime. So I'm going to put all the terms with y prime over here and all the terms without y prime over here. Okay, so I'm going to go ahead and do that. Alright, first term does not have a y prime, so I'm going to put it on the other side, so I'm going to subtract it off. This one does have a y prime, so I'm going to leave it. This one does not have a y prime, so I'm going to subtract it off. This one does have a y prime, so I'm going to leave it. Yes, y prime, leave it. Alright, so there is the same equation, we just move some terms around. Alright, now notice that I have 1, 2, 3 y primes, but if I factor it out, I only have 1 y prime. Alright, so we're looking good now. We have only 1 y prime times all this stuff, so we're just going to divide by it. Alright, now I'm going to switch back to dy dx notation. I was being lazy by using y prime. But now dy dx equals -12x minus 3y over 3x plus 4y plus 17. And I'm going to do one other thing, just because it bothers me, having these two negatives on top. I'm going to factor that out. So it's going to be 12x plus 3y all over 3x plus 4y plus 17. All right, so that's what dy dx is. And remember, dy dx, this is an expression that gives us the slope of the tangent line. All right, so it goes through the point, the graph goes through the point, -1, 0, and this is our expression for the slope of the tangent line. So when we want to find the equation of the tangent line, we go back to the trusty old point-slope formula. And let's start to figure out what we need. We need a point, taken care of, and we need a slope, which is going to come from here. So the x and y values we're going to plug into this expression are -1 and 0. So we have a negative sign out front, 12 times x, so that's going to be a -12, plus 3 times 0, nothing, 3 times -1, 4 times 0, plus 17. Alright, so our slope is going to be, let's see, a negative and a -12, so we have 12 over 14. We can simplify that to be 6 over 7. All right, fantastic. So that's the slope of our tangent line. Great, so let's plug these things in. So y minus the y-coordinate equals the slope of the tangent line times x minus the x-coordinate. All right, so we have y equals 6/7 of x plus 6/7. And usually you guys add that 0, but obviously we don't have to worry about that. All right, so this should be the tangent line. All right, now let's figure out the equation of the normal line. Remember, the normal line goes through the same point in this case, because they tell us it goes through the same point, but its slope is going to be an opposite reciprocal. So let's do the same thing. Y minus 0 equals, now instead of using 6/7, we're going to use -7/6 x minus -1, which is x plus 1. So we're going to get y equals -7/6 x minus 7/6. And that should be the equation of the normal line. All right, as always, we want to try to think of ways we can check our work to see, and I figure no better way than GeoGebra. All right, so now we can see the ellipse that I had promised you. And the reason you had never seen that equation before is because when we had done ellipse in pre-calculus, this major axis, you know, the one that goes through the focus point and the vertex points in the long direction, this major axis was never slanted like this. It was always either horizontal or vertical. It was never slanted. But that's okay. You don't need that for this problem. But anyways, here's the graph of the ellipse that I promised you. Now let's plug in those equations we found. So we found y equals 6/7 x plus 6/7. And this was the equation of the tangent line that went through the point -1, 0. Let's see how we did. Pretty darn good, right? This looks to be tangent here, only going through one point, and it looks like that one point is -1, 0. Looking good. Let's try our normal line, which was y equals -7/6 x minus 7/6. Normal line, looking good. Excellent, going through the same point. It looks like it's probably a 90-degree angle here. Let's double check. Yeah, excellent. Okay, so this was an example problem of implicit differentiation. Remember, we need to do that when the x's and y's are all jumbled up on the same side. If you have any questions, please write them down and bring them to class. Have a good one.